There's a green line that's parallel to this one. Just as you can see, there's only one of them. W transpose X plus B equals -1 on this side, and on the other side, W transpose X plus B equals 1. And later you'll see, and I'll talk about it, that this point and this point are the support vector points. Because they're on this boundary, it's like imagining two countries with a border guard in between, and this is what separates them. That's what's happening here. Of course, here, please also note that I've used other classifiers as well. Just as you're aware, this classifier is actually a very poor one because it hasn't been able to separate them properly. What I mentioned here is just one classifier. Let me tell you, the goal is to maximize this margin, which is what has happened here, right? So here, this hyperplane of mine, W transpose X plus B equals 0. This other hyperplane, because it's for this side, W transpose X plus B equals 1, and on this side as well, W transpose X plus B equals -1, and you can see precisely that when you have an A transpose X. In addition, when you have a transpose X plus B equals 0, this one can also be greater than or equal to 0, which forms a half space. Or it can be less than or equal to 0, which forms another half space. The intersection of these two half spaces is actually this hyperplane, and their union is what? R in general. So, what's the goal? Mr. For example, what's the main objective?
We haven't specified the margin yet.
All right, Mr. Rizai, what are our constraints? What are our limitations?
We assign a level of 1 to the data points above this classification line, and a level of -1 to those below the classification line.
Yes, as both of our dear friends mentioned, that was absolutely correct. They said, what is our main goal to maximize? It's the margin. Let me say it again. Our main goal is to maximize the margin, which is the margin we've already explained in detail. So we had two labels, 1 and -1. As I mentioned, in this space you see here, W transpose X sub I plus B is greater than or equal to 1 here. And W transpose X sub I plus B is less than or equal to -1. Let me tell you, it's in this part, okay. It's become very straightforward. It's a mathematical model, and now we need to formulate it. Our goal is to maximize this margin, or boundary, along with our constraints. So if y sub I equals 1, then this relation holds. If y sub I equals -1, then this one. Now, if meaning here it's either this or that, it's either this one or not, or it's the other one. So, how can we write this as a mathematical model? Should I get into this now? So, what I want to do is present to you the formulation, which is also the primary problem. Before I do that, there are a few points which are mathematically quite simple that I need to mention to you. First year. Let's consider this line. Transpose of X plus B equals 0. What is the distance from this line to the origin? If we want to calculate this, the answer is the distance from this, well, in higher dimensions, it's a plane, but here it's a line, to the origin is equal to the absolute value of B divided by the norm of W. Here, as we know, since we have different types of norms, which have also been explained in previous sessions. Here, for our discussion, we are working with the 2 norm, which is the Euclidean norm. That's what we're using. If we want to do this, how can we prove it? It's actually quite simple. As you know, W is essentially the normal vector or the gradient vector. We've already explained this in previous sessions. It's a vector that's perpendicular to this line. It's perpendicular to this hyperplane. As you can see, W is perpendicular to W transpose X. Plus B equals 0, as we can see here. All right, the first thing we do, very simply, is to find the distance of a point like x0, just a point like x0. We take a point like x0 on this line. When you take a point like x0 on this line, or on this hyperplane, so what happens in this case? It satisfies the equation. So here, as you can see, W transpose x0 plus b will be equal to 0. All clear? Well, it's pretty clear that the vector W is perpendicular. The normal vector, the gradient vector, is perpendicular to what? To this line. Now, so k times W equals what? x0, right. It's pretty obvious, you can see here, so k times this W equals what? It's x0. Okay, so what's the value of k? It's pretty clear. Let me show you how to do this. kW equals x0. And is this also W transpose x0 plus b equal to 0? So instead of x0, it's kW. K is a scalar, so it comes out and becomes W transpose W, right. Pay close attention. W transpose is a 1 by n vector. W is an n by 1 vector. And the result of their multiplication is, these are scalars 1 by 1. All right, so kW transpose W plus b equals 0. So what was the goal? Friends, the goal was to find k, so we bring it to this side and it becomes negative b divided by W transpose W, as you can see, and you know from linear algebra that W transpose W is actually the norm of W, specifically the L2 norm squared. So k equals negative b over W transpose W, and what do we substitute for that? We use the L2 norm of W squared. All right, so k takes this form. It comes out in this form. So from here, if we take the norm on both sides, the norm of x0 equals the norm of k times W. Now we know k is a scalar, so it can come out of the norm as its absolute value. That means this is in the form of the absolute value of k times the norm of W. All right, so the norm of x0, the magnitude of x0, which is what we have and what we're looking for, is equal to the absolute value of k. In the norm of W, friends, what is k? It's negative b over the norm of W squared. We substitute that in and take the absolute value. From here, as you can see, the absolute value of b and the norm, which is a positive thing. So, as you know, this W cancels out with one of these Ws, and the norm of b over the norm. Sorry, let me correct that. The absolute value of b over the norm of W. So, if we have W transpose X plus b equals 0, its magnitude will be the absolute value of b over the norm of W. Now, for example, if this becomes W transpose X plus b equals 1, it's pretty clear. We write this as W transpose X. Plus, in parentheses, b minus 1 equals 0. So, what does this amount become? It's the absolute value of b minus 1 over the norm of W, just to clarify. That's how it is, right? Okay, now let's move forward. Because I want to calculate the margin, it's like I have 3 lines, or 3 hyperplanes, to start with. Here, we also see the distance. We want the distance between 2 parallel lines or hyperplanes. Let's see how it works. It's really simple. I mentioned it here. Is it the absolute value of b over the norm of W? Here, I also said we move b to the other side, so it becomes W transpose x plus b minus 1 equals. So, what's the value of this? It's the absolute value of b minus 1 over the norm of W. All right, and on this side, it was the absolute value of b over the norm of W. So how does this distance work? So how does this distance work out? It becomes this distance minus that distance, right? What was the size of this distance? We wrote it down. It was this. What about the size of that distance? That was it. We wrote it down. Well, this is obvious. It's just a simple math example, and it's also an absolute value. So, what's the distance between these two values? 1 over the norm of W. Well, we also had another one on this side, which was W transpose x plus b equals negative 1. This one is also pretty obvious. So, it was like this, basically. I'll bring it to this side to make it equal to 0, since it was equal to negative 1. This one is also the absolute value of b plus 1 over the norm of W. Obviously, the distance from this to the other one is equal to what? It's 1 over the norm of W. So, if you call this distance d1 and the other one d2, and you want to maximize them, what are these two? They're equal, as you can see. It's pretty obvious. I've got AD1 and AD2, and I want to maximize them. What? The margin. So, what's the margin, friends? One is D1, the other is D2, so what does that mean? Friends, the maximum is D2. Well, how much was D1? It was. How much was D2, which was equal to D1? So, the sum of these becomes what? What? Please be precise from the perspective of optimization, which I've explained before. Different types of problems are equivalent to each other. This maximization problem is equivalent to the minimization of W, and it's also equivalent to minimizing 1/2 of W squared. So, what can I do with this in this form? Can I write it like this? Please pay attention. Maybe the question comes up, why is there a 1/2 here? As is clear and obvious from the mathematical operations, when you want to take the derivative to get the gradient here. Because this is in the form of 2W prime, what do we want to do with this 2 and this 1/2? That's why, in optimization problems or in optimization tasks, we try to use this 1/2 of W squared, W to the power of 2. So my problem changed from a maximization problem of 2 over the norm of W to an equivalent problem, which is minimizing 1/2 of W squared. What is the norm of W squared? What happened? It was transformed and changed. All right, let's move forward. What do I want to do? What should I do with the initial or primal model? How should I write it? How does it work? Let's keep going. It became like this. Minimize an objective function. Minimize a function that I explained before. F of x, subject to a set of constraints. Now, for example, in the form of g of x less than or equal to 0, or greater than or equal to 0, this is an optimization problem. I want to put it in this form. So, friends, what does it become? This problem, in the form of 1/2 W transpose W, what is that? That was our objective function, and our goal was to maximize it. It was about maximizing the margin. So, what does this become equivalent to? Minimizing 1/2 W transpose times W. Now, here, regarding the constraint, there's a very technical point that you need to pay close attention to. And this is a clever move that Vapnik and his colleagues made. What did they do? They actually did this. So Vapnik and his colleagues thought about it and said, what if? Is it Einstein's W transpose X plus B is greater than or equal to E? I'll highlight it in yellow here, so it becomes Y in this yellow part. So overall, in this, W transpose X underscore I plus B is greater than or equal to what? Y underscore I, and Y underscore I is 1, so it all works out. Alright, so it says, should we multiply from this side too? Let's see what happens. The main goal is this. How can we turn two sets of constraints into a single set of constraints? Somehow combine them so that it becomes an OR situation and do something with these. This is something that, in optimization, in operation research, this normalization technique is used a lot. So, we multiply Y underscore I in this yellow part. It becomes Y underscore I times W transpose X underscore I plus B for the inequality direction, because Y underscore I equals -1, the direction of the inequality changes, and it takes this form. So, all our constraints are now in what form? Y underscore I times W transpose X underscore I plus B is greater than or equal to 1. See how nicely this problem has turned out. From an optimization perspective, this is a really elegant problem, and I'll explain more about it. I've talked about this before, too. Did I go over quadratic programming with you? Did I explain how it works? Folks, this is a quadratic programming problem, and you'll see why I'm giving a brief explanation. I explained it before as well, didn't I? It's really important to know this point about the problem. And this is a strength of support vector machines. They have a global solution. This is a very important point. This problem has a solution, and what kind of solution is it? It's global, and we'll also discuss under what conditions it will be unique. In other words, it will have a unique solution as well, under certain specific conditions, which I'll mention, but the important point is its global minimum, which was pointed out here. We know this. QP methods are those that were explained in previous sessions and in the background. They were explained in the mathematical background. In the mathematical background, it was explained that there are very good methods for solving them. There are powerful mathematical methods, and there are also excellent packages both in Python and in MATLAB or other software that can be used for this purpose. For example, there's QuadPro in MATLAB, which is used to solve this problem. The point you need to pay attention to is, what is the goal? The goal is to find W and B. We'll talk about it somewhere else. It's not really necessary to get into it right now, but that's our overall goal. First, let me explain this. Why is this a quadratic programming problem? It's because, as I mentioned in the mathematical background sessions, this is an example of quadratic programming. In the form of 1/2 X transpose QX plus C transpose X plus D. That's it. If you consider it this way, this problem is a quadratic programming problem. This is the form you can see here. When we talk about X transpose QX, Q is a symmetric matrix. And it is positive definite. It's discussed in this method, and in the previous form you saw that your C transpose X, your C transpose is 0, so we don't have anything like that here. You also didn't have Gx equal to G here. If you look closely, if you multiply this part by a negative, meaning if you multiply this part by -1, X less than or equal to B becomes greater than or equal to, and it turns into the greater than or equal to form. The important point here is that, in that problem, if you set Q to I, the problem we had here. Here, if you set your Q to I, the identity matrix, and let me tell you that. And if your X transpose is W, then it becomes W transpose IW 1/2. What form is this? It's quadratic. That's why, folks, we call it this. It's a quadratic programming problem, or in other words, a quadratic problem. So, it's a quadratic programming problem. You know that for a linear programming problem, for example, you can use the simplex method. We use linear programming methods to solve it, but here, again, we have a quadratic programming problem. As I said, there are very good and efficient methods available to solve this, and that's the reason. Maybe that's why. One of the reasons for the popularity of the SVM method, support vector machine, which we use, is because of this. All right. We want to solve this problem. How do we solve this problem? One of the classic methods, which was previously explained to you in the mathematical background, is to use Lagrange multipliers to solve this problem. Lagrange multipliers have also been explained. And this is the Lagrangian method. What is the Lagrangian method? It was explained before, but maybe at that time, since you hadn't seen the problem yet, you didn't pay much attention to it. It's a problem of minimizing a function. So just look at the goal. What I'm talking about is the Lagrangian method and then the Lagrange multipliers. Why are these being explained? They're for solving this specific problem for our primal problem. For that, it's just 1/2 W transpose W. Let me say this here once more. Because this is very important, what method do we want to use to solve this problem? We want to use the Lagrangian method. The Lagrangian method in mathematics. As well, you were already familiar with it, and I've explained it too. But here, since we want to use it quickly, I'll explain it one more time. For example, let's consider an optimization problem, friends, that consists of two types of constraints. Some of its constraints are in the form of less than or equal to a certain value. Some of its constraints are in the form of equality. So here, as you can see, you have M1 constraints in the less than or equal to form, and M2 constraints. What are they? They're in the form of equality. Pay attention, someone might ask, why don't you have any greater than or equal to constraints? That's actually very simple in operations research. We just multiply everything by -1 and turn them all into less than or equal to constraints. That's why I wrote these two types. Alright, friends, we want to solve this. As explained in previous sessions, we define the Lagrangian function in this form. F of x plus the sum from I equals 1 to, how many was it? Up to m1, lambda I, yix, plus the sum from I equals 1 to m2, vi. Hix, meaning corresponding to yix. We define a number of variables corresponding to what? To the constraints. We want to define variables called lambda i's, and they correspond. For these equality constraints, we define a set of variables called vi. What do? I define them. So, our problem in the form, meaning a constrained problem, how does it become an unconstrained optimization problem? It gets transformed, right? So, what do I do with this optimization problem? I turn it into an equivalent optimization problem. I transform it. Now pay attention here. I have the lambda I coefficients and what else? The vi's, which I've brought in here. What do we call these? These are called the Lagrange multipliers. Southwest, pay close attention. Because here, since it's less than or equal, what lambda i's be? They must be positive. Here, since the hix's are equalities, lambda i's are unrestricted. So here, pay close attention to lambda i's. For the reasons we've discussed before, and because this is an optimization problem, and we're trying to minimize it. What should these lambda i's be? Should they be positive? And here, your vi's can be what? They're free without any constraints, meaning they can be either positive or negative. It doesn't matter. So fx in the form of lambda transpose times s plus v transpose times s. What does s become? Okay, let's pay close attention here. Here, y underscore I times w transpose x plus b is greater than or equal to 1, meaning 1 minus this is less than or equal to 0. So there are a set of constraints, the number of which is equal to the number of your training points, where I goes from 1 to n. The number of training points we have here, what are they? Let me tell you, you can write them as less than or equal to constraints, or even as equalities. At the moment, we don't have that here, so let's move on. Alright, now we've entered the discussion of the dual form. I've talked about Lagrange multipliers, the Lagrangian method, and before that, the quadratic programming method. I've explained that. Alright, let's get into it and see what's going to happen here. What was the objective function? Minimize 1/2 w transpose w, or 1/2 the norm of w squared. The constraints. How is it set up? Y underscore I times w transpose x underscore I plus b is greater than or equal to 1. So this was our objective function. Our constraints are as follows. The corresponding variables. With this constraint, which are our Lagrange multipliers are alpha underscore I. We consider them. Well, because I had written it in the form of g underscore I x over there. Less than or equal to 0, it was in the form of less than or equal to 0. Here, let's be precise. I write this in the form of 1 minus y underscore I times w transpose x underscore I plus b. So it takes this form. Your g underscore I x is less than or equal to 0. The Lagrange multipliers are the alphas. Alpha 1 corresponds to sample 1, alpha 2 corresponds to sample 2, up to alpha n which corresponds to sample n. So the problem is in the form of 1/2. It's a minimization problem in the form of a minimization. Because what did we want to minimize over? We were paying attention that we wanted to minimize over w and b. So the problem is in the form LPA, the equals 1/2 w transpose w plus sigma. How many was it? From 1 to n, which is the number of our observations or our training samples anyway. Is there a transposable x from 1 to the other alpha I in the first of the transposable x and w? Plus its b. This is exactly the form you use when you press w and b. I already explained that you want the poison of the Lagrange more than w and b. Minimize. What do we want you to do with alpha? Maximize. It's exactly in this form, and it's very clear too, because the alphas correspond. With these, what did we say the alphas are? They're positive, so for this to happen, since 1 minus this is less than or equal to 0, basically you have to. What do you have to do here? You have to maximize your alphas. This is a completely straightforward optimization problem that has already been explained. So what is it with respect to? Should we maximize with respect to alpha and minimize with respect to w and b? the solution to this equation, what kind of equation is it? Basically, it's a saddle point solution or a saddle point. What is a saddle point? I'll explain that in detail. Since this problem, as previously explained, is a convex problem, it's convex, so you can actually swap the min and max. Please pay close attention to this. You can't just swap the min and max anywhere you like. Here, because of the convex property, you can do this. So minimizing over W and B and maximizing over alpha is the same as maximizing over alpha and then minimizing. It's like this. Are these two equivalent? I said, what is this? It's a saddle point. You're at a saddle point. What's a saddle point? That's been explained as well. I'll introduce it to you again. It's in the mathematical background. It was discussed in that session. Consider this point, friends. It's very clear. This point is a saddle point. Because when we consider this part, let's look at it this way. In this direction, what happens? It gets minimized. And when you look at it from this direction, what happens? It gets maximized. That's why it's called a saddle point. So, for this reason, here you have a min-max or max-min problem. As I said, with convexity, you can switch the order of these two. I've emphasized this several times because, as a background, mathematically, it's definitely